Hello students, good time to all. I am Chandan Kumar Pradhan. Welcome to YouTube channel Chandan Physics. In this video, we are going to discuss Saha's ionization formula and its derivation. Let's begin. Meghnad Saha, one of the greatest Indian astroscientists. According to him, Saha's ionization formula is a relation which relates the ionization state of a gas in thermal equilibrium to the temperature and pressure. Ionization state of a gas in thermal equilibrium to that of temperature and pressure. Basically, this is an expression between the free particles and those bound in atoms. Mathematically, n e square divided by n minus n e is equal to 2 divided by lambda q g1 divided by g0 e to the power minus epsilon divided by kBt. What are these terms? Where epsilon is the energy of ionization, S Planck's constant, Kb Boltzmann constant, T temperature, lambda thermal de Broglie wavelength, and that thermal de Broglie wavelength is equal to h square divided by 2 pi m e kBt under root, and n is the electron density, or we can say that is number of electrons, either in terms of density or in terms of number, and n is the either total density of the particles present in that of system, or we can say that is the number of particles. G0 degeneration of ground state and G1 is the degeneration of excited state. As we consider a two energy level system, so one is ground state and another one is excited state, and that excited state number as first excited state, and that first excited state again G1 number of degeneration. Okay. Another term Me, it is mass of an electron. Mass of an electron. These are the terms to that of equation. That equation is Saha's ionization formula. This one is Saha's ionization formula. What exactly Saha's ionization formula signifies? As we see stars, in stars it produces huge amount of energy. One of the example of star is our sun. According to Saha, the temperature is extremely high and the elements present inside that of stars are in the atomic state, and the most of the particles present inside the interior of stars undergoes frequent collisions. During that collisions, what happened? They are stripped of valence electrons. Look here, basically the stars are made by hydrogen. Since stars are made by hydrogen, so we consider For a hydrogen atom, when it's ionized by producing an electron, means it is excited, or we can say it is ionized. That ionization occurred in case of stars due to the collisions of hydrogen and hydrogen atoms in that of star at high temperature. Similarly, if that ionized hydrogen atom again captured an electron, then it converts to its neutral state. Okay, means first hydrogen collide and these hydrogen are ionized, again that ionized hydrogen atoms captured to an electron and transformed to its neutral state. What exactly that phenomenon indicate? The phenomenon of striping of valence electrons is known as thermal ionization, which is accompanied by electron capture to form neutral atoms. Basically, by considering that hydrogen atom, we derive Saha's ionization formula. For hydrogen atom, see the energy level, where n is equal to 0, here n is equal to 1, that is the ground state, that is the excited state. Since it is an 2 energy level system, that ground state again splitted upon G0 number of degeneration, and that excited state have the degeneracy G1 number of degeneration. The 2 level energy system. When at that of case, that is for hydrogen, when the velocity of electron is 0, we select that the ionization energy will be 0. For n is equal to 1 at first excited state, we consider the ionization energy E, which is equal to minus I, let for n is equal to 1, and that ionization energy can be calculated by using Bohr's energy equation. From Bohr's energy equation, that ionization energy epsilon is equal to Z divided by n square into minus 13.6 electrovolt, where Z is the atomic number, where Z is the atomic number. For hydrogen, that is 1. For hydrogen Z is equal to 1. Therefore, the ionization energy is equal to, for first excited state again n is equal to 1, that means minus 13.6 electrovolt. That amount of energy is the ionization energy for hydrogen atom. Let us derive the expression by using statistical mechanics concept. How we relate what be the number of free particles to that of bound in atoms. Okay. To derive such number, since hydrogen having 1 electron, 1 proton, a system considering 1 electron and 1 proton. Let the partition function for electron ZE is equal to summation over n e to the power minus e number of electrons Ne divided by kBt. Similarly, the partition function for proton Z P is equal to summation over n e to the power minus e, that is the energy for np number of protons divided by kBt. Next, partition function for hydrogen atom. The partition function for hydrogen atom, that is Z hydrogen is equal to summation over n e to the power minus e, that is number of hydrogen Ns divided by kBt. These are the partition functions. Now, the probability. Since the particles are indistinguishable in quantum mechanics, so the probability of what? The probability that the gas has Ne number of electrons out of total n particles, total n particles in an thermodynamic system, or we call it as in an ensemble. That is probability of any number of electrons out of n particles. The thermodynamic probability, since the particles are indistinguishable, the system has electron, proton, and for hydrogen atom we write it as the probability formula partition function Z to the power number of electrons Ne whole divided by Ne factorial for indistinguishable of the particles, into for proton Zp to the power Np divided by Np factorial number of protons. For hydrogen Zh, that is Ns whole divided by Ns factorial. Taking logarithm on both sides, taking logarithm on both sides, that is ln p is equal to logarithm formula first as Ne ln Ze minus ln Ne factorial plus here Np ln Zp minus Np factorial plus Nh ln Zh minus ln Nh factorial. Rearranging the terms as Ne ln Zd plus Np ln Zp plus Nh ln Zh minus ln Ne factorial minus, that is ln Np, here is the ln Np, ln Np factorial minus ln Ns factorial. These ln factorials are expressible by using Stelling's approximation, which one is Ne ln Zd plus Np ln Zp plus Nh ln Zh. Here Stelling's approximation is used, minus Ne ln Ne minus plus Ne, next minus Np ln Np plus Np minus Nh ln Nh plus Ns is equal to, again we can use Nh is equal to, we substitute Ne is equal to Np, number of electrons is equal to number of protons, and for hydrogen Nh it is total number of particles minus total number of electrons. This is substitutions we have to introduce there. Therefore, Ne ln Zd plus in place of Np that is Ne ln Zp plus in place of Ns that is N minus Ne ln Zh. Next minus Ne ln Ne plus Ne in place of Np that is minus Ne ln Ne in place of Np plus Ne minus in place of Ns that is N minus Ne ln Ns as N minus Ne plus in place of Ns N minus Ne. Now differentiating that logarithmic term with respect to Ne, differentiating with respect to Ne, we get so d ln p with respect to Ne is equal to the first term as ln Zd ln Zd, next term ln Zp. In that term, first term as ln Zs minus Ne as minus 1 minus ln Zs. Again here differentiation of first term, second term as constant, differentiation of second term, first term as constant, differentiation of first term, second term as constant, Ne differentiation as 1 minus ln Ne. Next differentiation of second term, first term as constant, so minus Ne 1 Ne plus Ne as 1. Next differentiation of first term, second term as constant, plus 1 again plus differentiation of that Ne as 1 minus in that section differentiation of first term, second term as constant, minus ln n minus Ne its differentiation minus minus plus 1 minus differentiation of second term, first term as constant, n minus Ne differentiation of that term 1 divided by n minus Ne minus 1 last term n minus Ne as minus 1. Now look here, Ne cancel out, plus 1 minus 1 cancel out, Ne cancel out, that is plus 1 minus 1 cancel out, again plus 1 minus 1 cancel out, here that term cancel out, minus minus plus, finally we obtain that is ln ZE plus ln ZP minus ln ZS minus ln NE minus ln NE minus ln NE minus ln NE plus ln n minus NE. Here we missed a term. Look here, for that NE ln NE, that is ln E minus that one, differentiation first term second term as constant, differentiation second term first term as constant, next NE differentiation as 1. Next in that term first we differentiate NE and minus ln E as constant, so minus ln E, next minus differentiation of first term NE ln E differentiation 1 by NE, next 1, like this it proceeds to that missing term now written here. Okay, this is for what? D ln P with respect to NE. First, for most probable macro state, that is in equilibrium condition, in equilibrium condition its differentiation ln P with respect to NE will be 0. Therefore, the term ln ZE plus ln ZP minus ln ZH minus ln NE minus ln NE plus ln n minus NE is equal to 0. Therefore, here taking ln ZE plus ln ZP minus ln ZH in that side, on another side ln NE plus ln NE minus ln n minus NE. Therefore, ln A plus B minus C, that is ZE into ZP divided by ZH is equal to ln NE into NE divided by n minus NE. On both sides log are cancelled out, so ZE into ZP divided by ZH is equal to NE square divided by n minus NE, taking as equation number 1. Let us evaluate what is the value of ZE, ZP and ZH. To calculating such one, first we have to consider a partition function in a particular interval. To calculate these terms, we have to consider the number of particles in the given momentum interval. That momentum interval, let dp and that dp interval between p and p plus dp. Within this momentum interval is taken as the particles have a continuous momentum distribution. Hence z for I, zi, that is integration over gi e to the power minus, for kinetic energy it is p square divided by 2m divided by kbt. For position dqx, for momentum dqp divided by hq, that is the partition function for continuous momentum distribution. gi, the degeneration of that of ith state. Here I represents, I is either E or P, either electron or proton. Is equal to here we can use dqp, that is 4 pi p square dp in that of integral. When we use dqp as 4 pi p square dp, the expression is written as 4 pi gi divided by hq, these are the constant terms, then integration over dqx, at the position integration. Next momentum from 0 to infinity, p square into e to the power minus p square divided by 2m kbt into dp. As we say, dqx is equal to v, that is the volume, then 4 pi gi into v divided by hq, integration over 0 to infinity p square e to the power minus p square divided by 2m kbt dp. Let us substitute, let us put y square is equal to p square divided by 2m kbt, and differentiating we obtain 2y dy is equal to, here 2p dp, 2 to cancel out, means p divided by m kbt dp, m kbt dp, or p dp is equal to 2m kbt y dy. All substitutions are now introduced in that of expression, that is 4 pi gi v divided by HQ, that is 2m kBT to the power half into integration over 0 to infinity 2m kBT y square e to the power minus y square dy, which is equal to, this is a constant term, that constant term also to that of outside, 4 pi GIV divided by HQ 2m kBT to the power 3 by 2, your half 1 3 by 2 integration over 0 to infinity y square e to the power minus y square dy. That the standard integral value 0 to infinity y square e to the power minus y square dy is equal to under root of pi divided by 4. So, in that of final expression for GI, it is as we put the value of under root of pi by 4. So, GI V divided by HQ 2 pi m kBT to the power 3 by 2, as we taken for electron and proton for I. So, GI be 2 for that for electron and proton, for electron and proton, as these are fermions. So, G for electron is equal to G for proton is equal to 2. Therefore, Z for electron is equal to 2V divided by HQ 2 pi ME mass of electron kBT to the power 3 by 2, and Z for proton 2V divided by HQ 2 pi mass for proton kBT to the power 3 by 2. But for hydrogen atom, G for hydrogen is equal to 4, and ionization energy term is introduced. So, Z for hydrogen is equal to 4V divided by HQ 2 pi m hydrogen kBT to the power 3 by 2 into e to the power ionization energy epsilon divided by kBT. Okay. Let us put these values as A, B and C in that of expression as we written in equation number 1. Therefore, equation 1 becomes, n e square divided by n minus n e, n e square divided by n minus n e is equal to the values of ZE into ZP divided by ZS. The values of ZE is values 2V divided by HQ 2 pi ME kBT to the power 3 by 2. Next, same thing, values N square, so it's square divided by here ZE into ZP, sorry, not square. First we have to show for proton 2V divided by HQ 2 pi MP kBT to the power 3 by 2. N minus Ne, that is ZS. ZS value 4V divided by HQ 2 pi mH kB T to the power 3 by 2 into e to the power epsilon divided by kBT. As you say, mass of hydrogen is nearly equal to mass of a proton. In place of mass of hydrogen, we can substitute mass of proton and the terms are cancelled out. So, the expression will be written like that: Ne square divided by N minus Ne is equal to V divided by HQ 2 pi Me kBT to the power 3 by 2 into e to the power, the term to that of numerator side will be minus epsilon divided by kBT. These terms are cancelled out. In place of mass of hydrogen, we substitute mass of proton. So, mass of proton, mass of hydrogen terms also cancelled out, only mass of electron will be there. Let us introduce now the partition function, that is G1 divided by G0, ground state to that of excited state. In that expression and rewrite it. So, Ne square divided by N minus Ne is equal to 2 divided by lambda cube G1 divided by G naught. 2 G1 divided by G naught is introduced in that of expression, e to the power minus epsilon by kBT, whereas lambda is the de Broglie wavelength, and that value of lambda is h square divided by 2 pi Me kBT under root. First we write the value of lambda. Now, the expression which is Saha's ionization formula. N minus Ne, the number of atoms which are neutral in that of system, and Ne, the number of atoms which are ionized. That ratio signifies the formula, which is Saha's ionization formula. In that of expression, we just introduce the partition function G1 divided by G naught, which is the degeneracy for that of 2 energy level system. 2 is introduced for that purpose as we considering hydrogen atom. So, here with the help of this video lecture, we understand the concept of Saha's ionization formula. What is Saha's ionization formula and what it signifies? Its derivation. Considering the partition function for electron, for proton, then for hydrogen, that is the combination of electron and proton, then its probability, and taking logarithm and using the concept number of electrons is equal to number of protons in that of hydrogen atom, and non excited atoms, non excited particles in that of hydrogen atom, which is n minus Na, and differentiating it with respect to Na, and finally for most probable macro state, which is in the thermal equilibrium condition, its differentiation as 0, and finally Na square divided by n minus Na in terms of partition function. For ith state, as taking momentum distribution, we obtain its partition function, and so for electron, proton and hydrogen, the partition functions are defined, and putting in that of equation number 1, we obtain this equation, and introducing to that of partition function for 2 energy level system to achieve the densities of the atoms, the expression which is nothing but Saha's ionization formula. So, with this useful and informative notes, let me wind up the session. Thank you.